This is a Raspberry Pi 5, and it is a seriously impressive piece of hardware, especially when you consider its size. With it, you can very easily create a very powerful and very compact little computer. In fact, I plan to use this particular Raspberry Pi 5 to create an awesome retro gaming machine capable of running all of your favorite consoles. But what if I told you that when you pick one of these up off the store shelf, you don't really get its true potential? You can dramatically increase the performance of one of these if you're willing to put in a little bit of work, or a lot of work. We're gonna see what it takes to squeeze every last little bit of juice that we can out of this Raspberry. So, what is the secret sauce? Well, we're gonna be water cooling it, because the lower we can keep the temperatures, the harder we can push the hardware and the faster it'll run our games. The first problem I have to overcome is that nobody makes a pre-made water cooling kit for the Raspberry Pi 5, which means that I'm gonna have to make my own. The first half is this pump, reservoir, and radiator combo that I got on Amazon, and it's actually meant to cool a 3D printer. The second half of the system is going to be this generic copper water block, which will sit on top of all the Raspberry Pi's heat generating components, something like that. This should keep everything nice and cool because water is much more effective at removing heat than air alone. But this copper water block has no way of attaching to the Raspberry Pi. In order for optimal heat transfer, we need as much surface contact as possible, and yeah, this is just not gonna cut it. So I need to create a custom mount for it. In order to do that, I created a 3D model of the Raspberry Pi 5's motherboard. It's not super accurate, but it's got all the critical stuff that we need. From there, I created a 4-legged mount that will hold the water block in place. So with all that figured out, I started printing out my first prototype. Thankfully, because it was so small, it didn't take very long to print. And I also made this little temporary backing plate that holds the Pi in place with brass standoffs. By carefully tightening down each screw, I now had the copper water block mounted directly on top of the Raspberry Pi's CPU. And it actually looks pretty good for a first draft. But I didn't think about one thing. Oh, crap. This is PLA plastic, and if you know anything about 3D printing, you know that this is not the material to use. As PLA heats up, it deforms, and it loses almost all of its tensile strength. So that means, as we're gaming and generating heat, our water block here is going to make worse and worse contact with the CPU, which is obviously not what you want. So, in order to fix that, I reprinted the part in a completely different material. This is carbon fiber reinforced nylon, and it can withstand temperatures of almost 200 degrees before it starts to deform, which in a worst case scenario should give us over 100 degrees of headroom. It's also significantly more expensive, so it's actually probably a good thing I did the early prototyping in a cheaper material. There we go, that eliminates any concerns I have about deformation. So next, in our search for ultimate performance, we need to take a look at the CPU. Many people think that this is the CPU, but it's actually just a thin layer of metal that covers the CPU. The actual CPU is under here somewhere. This metal is called the IHS, or the integrated heat spreader. And the problem with it is that it adds a layer between our cooling and our hot CPU. So I decided to remove it. I grabbed my trusty soldering station that includes a hot air gun, set it to a nice low temperature, and began loosening the thermal adhesive that keeps the IHS in place. As always, I'll include a link to it, along with all the other tools and materials that I'll use throughout this project down in the video description. Once I got things nice and hot, I used a knife to very gently pry up the IHS. The CPU die that sits below it is extremely fragile, so I took it nice and slow. One small slip of the blade and you can very easily brick your Raspberry Pi. Eventually though, it popped right off. Oh, there we go. And now we can see why it's so bad for cooling. That right there. That is very low quality thermal adhesive. So with a little bit of rubbing alcohol and some scrubbing, I was able to remove it. Now, a lot of people will replace this adhesive with a higher performance thermal paste and then just reinstall the IHS, but I think I'd rather get rid of it entirely. If I can find a way to get this block to make direct contact with the die, that will give us maximum cooling performance. But looking at it, I think we got some clearance issues. Our inlet pipe is hitting this little power switch here, and also our RAM chip and our CPU are at different heights. So it became clear to me that I was gonna have to modify my copper water block. These are 1mm thick copper shims, and by trimming them ever so slightly, I was able to fit 4 of them side by side over top of the CPU and the RAM. This will shift our CPU block up 2mm higher and give us clearance over that button on the Pi's motherboard. But obviously, we can't just stack them in place like that because there's no way they'll effectively transfer heat. So I set up to do a little bit of brazing. I started by painting on some flux. Not only does this stuff clear away any surface oxidation, which will allow us to join our pieces together with solder, but it also has the effect of pulling that solder into any small voids between the pieces, which will effectively give us one solid block of copper in exactly the shape we need. But looking at it, it didn't look great, and you can see that it was visibly, well, not very flat, but that's okay. I was prepared for that. I set up a series of progressively finer wet sanding stations on my workbench. I started at 400 grit and slowly sanded down the worst of the imperfections. I could have stopped there, but working my way down the bench, I was able to get a smoother and smoother finish on the block. And the smoother the block, the better it will transfer heat. I didn't quite get it to a mirror finish, but it's definitely better than the factory finish you'd get on most heatsinks. So with all that done, I headed back to my office to test out my new block. So I've got everything laid out in front of me that I need to test the system, but I'm realizing that I don't have any way to power it. Both the pump and the fan run on a 12-volt architecture, and then if you look down here, there's this little buck converter board that supplies that, which is fed by this standard barrel plug adapter over here. But I don't have one of those, and it didn't come with one either, so I'm actually just gonna convert the whole system to run off of USB-C, which is the same as the Raspberry Pi itself. Now, that might sound a little complicated, but it's actually easier than you might think. By using a USB-C power delivery trigger board and setting these dip switches, we can configure it to request 12 volts of power from a standard power delivery adapter, like this one that I got from Ugreen. A quick check with the multimeter confirmed everything was working correctly, and then I transplanted the wiring harness from the buck converter to the new trigger board. This whole process took less than 10 minutes and should make the whole setup a lot more convenient to use. But I still wasn't sure that my adapter would provide enough current to spin both the fan and the pump at the same time. So I set up to do a little bit of testing. Not the quietest fan in the world, if I'm being honest. Good airflow though. Now, definitely don't want to do this for too long. Just a second. Yep, there we go. Sweet. With the power delivery sorted, I was able to start connecting hoses and filling the system with distilled water, which is actually not the ideal coolant, and we'll be replacing it later. One thing you want to watch out for is that you don't accidentally airlock your system. It's pretty easy for air bubbles to block the small passageways inside the radiator, so as I'm adding water and running the pump, I'm also rotating and agitating the whole system in an attempt to dislodge any bubbles. Once I felt like I got them all, I let the system run and kept an eye out for any leaks. All right, our setup has been running for a little over an hour now. There are no leaks. It is still a little bit loud, which I attribute to there still being some small air bubbles in loop, so hopefully that'll quiet down later. But for now, I think we should get started on the software side of things, where I have some pretty cool stuff to show you guys. The first thing I did was take an SD card, plug it into my computer, and install Raspberry Pi OS on it. This is a pretty basic and stripped down version of Linux that's designed specifically for the Pi. I then transferred it to the Pi, ran through the initial setup, and got dropped into this pretty bare bones desktop environment. From here, I installed Geekbench 6 and some temperature monitoring software. Running Geekbench, we can see that pretty quickly the Raspberry Pi heats up to the mid 80s running at the stock 2.4 gigahertz. And using the thermal camera, we can see that, yeah, the top of the die is a bit cooler, but pretty much in line with that number. So now, let's see how it does with our water block installed. I used a little dot of Noctuous thermal paste on the CPU die, and then for the RAM chip, to eliminate that slight difference in height that I mentioned earlier, I used a small dab of K5 Pro. This stuff is similar to thermal paste, but designed to work at a much greater thickness. With it, you can bridge gaps up to 1mm. So with that done, I reinstalled the block and booted up the Pi to check out how much better my temps were. And even I was shocked at the difference. Whoa, that's a lot. Holy. Needless to say, I was very pleased to see that my custom water block had dropped the CPU's temperature by almost 60 degrees, which should give us a ton of headroom to push the CPU. I started with small incremental overclocks. The way you do this is by editing a little config file on the Raspberry Pi and then rebooting it. I went from 2.4 gigahertz to 2.6 gigahertz to 2.8 gigahertz, and I also slowly increased the voltage supplied to the CPU to help keep it stable. I pushed it to a nice round 3 gigahertz, and even that only managed to raise the CPU's temperature by a degree or two at most. But that is where I hit the wall. Just not in the way that you might think. I still had a ton of thermal headroom, but I couldn't go even 10 megahertz higher. Turns out the firmware on the Raspberry Pi 5 caps the CPU's frequency at just 3 gigahertz, which was very annoying, so I went in search of a solution, and I think I found one. By forcing the Raspberry Pi to update to a beta version of the firmware, I should be able to remove that cap. Okay, let's see. If this says 3.1 gigahertz, I'm going to be very happy. Duh. Yes, 3.1 gigahertz. Okay, we're through the barrier. Now we can see how far above 3 gigahertz we can get. Unfortunately, further testing revealed that 3.1 gigahertz was just about the limit of this particular CPU. I was able to squeeze a tiny bit more out of it, and a good bit more out of the GPU too, but anything more than that and the system would just lock up during benchmarking. Given how low our temperatures are, we must be voltage limited, and annoyingly, the firmware caps the max CPU voltage at just 1 volt. Hey everybody, it's Future Zach here. So I was basically done this project when fellow YouTuber Jeff Geerling released a video showing how to remove that voltage limit. With some very clever scripting, you can actually raise the voltage limit to 1.1 volts, which is a considerable increase. So not wanting to leave any stones unturned, I went back and followed his instructions to see if I could push my little Pi here any further. And yeah, the results weren't great. Even with the increased voltage, I couldn't get any higher than 3.2 gigahertz, and I think what that comes down to is just the good old-fashioned silicone lottery. Some chips are just better than others. Obviously, I was hoping to get more than that, but if you consider where we started from, I still think 3.2 gigahertz is a pretty sizable increase. So now that we've found the limits of our setup, the next thing that I want to do is, well, honestly, the next thing I want to do is get right into gaming. But before we do that, I think we should create an enclosure to make this look a little bit more cohesive and more like an actual game console as well. And to be honest, this was a pretty tricky design exercise. I had a lot of different parts that I had to account for, and I wanted this thing to be as small as possible. So the first thing I did was measure and model all of my main components. This might seem a little unnecessary at first, but it allowed me to try out a number of different orientations and find the best possible configuration. I eventually settled on this one because it gave me a relatively tight footprint, and with the right case design, should give me good access to all the components in case I need to fix or replace anything later on. Now, before we get into the designing and printing of the case, first I want to tell you guys about something that I found hugely helpful in this project, the Eufy S1 Pro, because Eufy is also the sponsor of today's video. The S1 Pro is the world's first and best floor washing robot vacuum. The 3D printing process left a bunch of small plastic debris on my office floor, but thankfully I had the S1 Pro configured to clean my office every night once I was done filming. In fact, it cleans my entire house. And you might be thinking that I've seen mopping robot vacuums before, so how is the S1 Pro the first or the best? Well, most mopping robot vacuums use either a vibrating or a rotating mop pad. But Eufy's designers realized that those systems often just kind of spread the mess around. So instead, the S1 Pro uses a rolling mop head that cleans itself with every revolution, ensuring top-notch cleanliness and efficiency. It also has a square body design that allows for the industry's widest mopping roller and the best possible edge cleaning capabilities. And creating a square robot vacuum was no small feat. They had to completely rewrite all the pathfinding algorithms to accommodate that new shape. But what it all adds up to is a robot vacuum that actually washes your floors instead of just mopping them. You can see I set up this test area with various tough to remove messes, and the S1 Pro completely cleaned the floor with nothing left behind. It's also got this really cool looking base station that pulls dust and dirty water out of the robot after every cleaning cycle, and then refills the robot with ozonated tap water that it creates in this tank that naturally disinfects your floors. And then probably my favorite feature of the S1 Pro is its 3D Matrix Eye obstacle avoidance system. The S1 Pro will map and navigate around your home using LiDAR, but it also has another AI-powered system that uses a combination of infrared and conventional imaging to avoid accidentally sucking up anything that it shouldn't. So if you want more information about the S1 Pro, or you just want to get your own, check out the link down in the video description. And now let's get back to designing and building this case. The first thing I did was design a super simple prototype enclosure. Basically, the only thing I'm trying to do here is make sure that all my models line up with reality. So I'm testing to make sure my screw holes and my USB ports line up. Sure enough, there were a couple of small things that I had to change, and I figured while I was making another prototype, I may as well solve the issue of the Raspberry Pi's ports. Looking at the motherboard, you can see that there are ports along two sides, but I want all of my wires to come out the back of the case. So I added these short extensions that allowed me to reroute them. I modified my case design to create some openings for them along with the trigger board, and then did a quick test fit. So there we go. With a couple of quick design iterations, we have all of the hard work done, and now we can get on to, well, kind of the fun part of the case design. Like I said earlier, serviceability was important to me, so I opted for a split shell design. My first attempt split the case like this, but I quickly realized that that was just way too complicated and didn't work very well. So instead, I opted for two interlocking U-shaped pieces, which worked a lot better. The next problem I had to tackle was airflow. Sure, I had the front intake, but I didn't have anywhere for that air to go, so I added all these little exhaust cutouts on the back side. I also wanted all the internals to be visible, so I added cutouts for some acrylic windows. And then, just to give it a little bit of visual flair, I embossed the Raspberry Pi logo on the top side of the case. Finally, I reworked the entire front face to make it both better looking and more functional. But rather than showing you a low resolution render, I'd rather just show you how I made it. So while my 3D printers worked on printing the revised case, I hit up the shop to get started on that. The first thing I did was find some fresh walnut and prep it for the CNC. Because it's such a small piece, I added some double-sided tape to prevent my CNC from turning it into a projectile. The initial shape here is pretty simple. It's just a big round opening that's the same size as the fan. To add some dimension to it, I headed over to my router table and used a chamfer bit to add a slight bevel to all the exterior edges. In theory, this might also make the fan a little quieter too, but I've got something much better planned for that later. A quick oil rub finish sealed the wood, and to my eyes anyways, gave it a much nicer finish as well. And while the CNC was still warmed up, I also cut the two acrylic side windows that I mentioned earlier. As always, make sure that you get cast acrylic instead of extruded acrylic for use on the CNC. It cuts so much nicer and won't crack or chip on you. The next thing I did should hopefully save me quite a bit of time in the future. If you've ever opened up an old game console, you know that these things are basically just big dust traps. So in order to prevent that, I got this fine metal mesh that I plan to use to filter the front intake. It's thin enough that I could just mark out what I needed and then flex it along those lines until it snapped. At first, I temporarily tacked it in place with some CA glue, and then once our case is done printing, we'll be able to fasten it more securely. But first, I've got to solve another problem. The fan on this system is just way too loud. For reference, it's generating about 46 decibels of sound and has a pretty annoying pitch to it. So to solve that, I went out and bought this ultra quiet fan from Noctua, which was actually so quiet that it failed to register on my noise meter. It probably doesn't move quite as much air, but given our completely overkill cooling setup, I really don't think that's gonna matter. Unfortunately, both fans, despite having the same operating voltage, have different connectors, so I had to do the old switcheroo, which in this case was just a matter of splicing the old connector onto the new fan, soldering them together, and then sealing everything with some heat shrink tubing. And then finally, after all of that, the case had finished printing. Again, I didn't want to use the standard PLA, so I opted for carbon fiber reinforced PETG. This stuff should be much more heat resistant. And because it has crushed up carbon fiber in it, it's got this super cool matte finish. But I'm sure you're asking yourself, what is that green colored plastic that's also in there? Well, that is support interface, and it's basically just a thin layer of a second plastic that sits between the support structure and the actual print. This stuff makes it way easier to remove your supports and gives you a much nicer surface texture where they interface. After I had all of that pulled off, I installed my acrylic windows with the help of some CA glue and then screwed the front intake panels in place, which permanently sandwiched all three layers together. I then started installing all of my components inside the case, which was truthfully a bit of a make or break moment for me. There were dozens of variables here, and I still wasn't 100% sure it was all gonna line up correctly. To my surprise though, everything actually fit together really well. And honestly, I think that's because I took the time to model each of my individual parts before I designed the case. It was definitely a bit more upfront work, but in the end, I think it saved me a lot of time. The last step was filling the loop, and here I'm hoping to gain back at least a little bit of the performance that was lost with our quieter fan. This is a specially designed coolant, and I actually had it left over from my water-cooled desk project. Not only does it have a bunch of additives in it that prevent corrosion and fungal growth, but it also has an additive in it that makes it more effective at transferring heat. So after burping the system a few times, I left everything running to work out any little micro air bubbles, and I got ready to do the fun stuff. So before we install the other half of the case, I'm gonna pop the SD card out of the Raspberry Pi. We're gonna format it to remove Raspbian OS, and instead we are going to install an operating specifically designed for gaming, Batocera, or Batocera. I don't know how you say it, but apparently it's supposed to be really good. And here's the cool thing about Batocera. Instead of using a traditional desktop environment like the Raspberry Pi OS, it's got a stripped down, lightweight launcher that's specifically focused on gaming, which makes it a lot easier to use as a game console. Once you boot it up, you are greeted with this screen where you can see all the different systems that our Pi can emulate. It also makes it really easy to transfer over games because Batocera just appears like a computer on my network. So all I have to do is drag and drop ROMs into their respective folder on my desktop, which I suppose is a good point to mention that obviously it's illegal to use ROMs that you don't actually own. I'm definitely not endorsing piracy here. So everything from the original Atari to the Super Nintendo, Genesis kind of era runs flawlessly here. And I don't think that's a surprise to anyone. These games all look and feel great, and it's honestly probably where I'll spend most of my time. Then getting into systems where the previous Raspberry Pi 4 struggled, like the N64, the Sega Dreamcast, and the PlayStation 1, well here, things are looking really good. The Raspberry Pi 5 emulates these systems without breaking a sweat. And honestly, you don't need to go to all the effort of water cooling and overclocking your Pi to get these systems to play just like they did back in the day. But that doesn't mean that our extra work here was wasted, because one of the best parts about emulating these old systems is that you can actually make them look a lot better. We can do all sorts of fun stuff, like cranking up the rendering resolution. Here, I was able to render the original Sonic Adventure at 2.5 times its original resolution, which makes it look just so much better. You can also add smoothing, anti-aliasing, texture filtering, and all sorts of different stuff. And the only limitation here is how much computational horsepower you have. In fact, some games are easier to run than others, even within the same system, so you often have to dial in your specific enhancements on a per game basis, which if you're a geek like me is actually kind of enjoyable. But the point is, our crazy overclock allows us to push these enhancements even further while still getting a smooth gaming experience. So an overclocked Pi will actually look better than a non-overclocked one, which I guess kind of brings me nicely to the next reason as to why an overclock is so important: the systems that came out after the ones that we've already mentioned. The first two I'll talk about are the GameCube and the Wii. Yeah, that's right, it's possible to emulate both of these systems on the Raspberry Pi 5. Kinda. It really comes down to which games you want to run. Some games are great and run buttery smooth, but others require more graphics processing than this thing can handle. Like in the Legend of Zelda Wind Waker here, the grass here kind of kills my FPS. That being said, because this Raspberry Pi 5 is over 30% faster than a stock one, it's the one you want to be using when you're playing games that are right on the edge of what's possible. That overclock might be the difference between your favorite game actually being playable or not. And then speaking of being right on the edge of what's possible, the PlayStation 2. Oh man, okay, this was an ordeal. So earlier versions of Batocera had support for the PS2 baked in, but at a certain point, the devs removed it because they felt like the Raspberry Pi couldn't handle it. So as configured, this system right now cannot play PS2 games. However, I thought that maybe, just maybe, my turbocharged system might be able to do it. So I went in search of a solution, and I found out there's this emulator called Aether SX2 that will work on Linux. So I went back into Raspberry Pi OS, tried to run it, and it just wouldn't work. So I did some more research, and everyone said that it works best in Ubuntu, which is a very popular desktop version of Linux. The problem is the latest release of Ubuntu was glitched and wouldn't load on my Raspberry Pi. Even more research later, and I found out that there's a way to fix that bug by editing a config file. After a lot of swearing, I eventually got Ubuntu running, did a bunch of terminal commands, which I barely understand, and finally, I got my PS2 emulation running on the Raspberry Pi. And what did I find? Well, I found a new appreciation for Windows and macOS because Linux is really annoying to use sometimes. But on the gaming front, well, the results are kind of similar to the GameCube and the Wii. Some games work and others are a struggle. Generally speaking, games that run at 30 FPS are usually better, and games that run at 60 FPS are usually worse. Overall, it's just not quite there, and I can understand why the Batocera devs removed support for the PS2, but I also feel like with a bit of optimization and a little bit more development, PS2 emulation might just be within reach of the Raspberry Pi 5. But yeah, right now, I would not recommend it. So, was it all really worth it then? If all you care about is gaming, then no, probably not. You could grab a Raspberry Pi, get a cheap off-the-shelf cooler, and probably get like 90% of the performance I did for a very small fraction of the effort. But as far as projects go, it was 100% worth it. Not only did I level up my 3D modeling skills, but I also learned an absolute ton about Linux, emulation, material science, and a whole host of other small lessons. Now, normally I do a post-mortem analysis right now, but I've actually decided to do those as separate members-only videos, and I've explained my reasoning in a community post linked down below. So become a member if you want to see that, get early access to videos, see sneak peeks of upcoming projects, and hopefully some other fun bonus content. And on that note, I will see you guys in the next one. Peace.